Hi everyone, it's Mrs. Martello. We're going to look at another example from section 4.2. I'm on page 184. And again, this is section 4.2. We're going to look at example 4. This is modeling with mathematics. So this is another real world example, but they add an extra layer in this question. So let's take a look at what we have. It says the student council is ordering customized foam hands to promote school spirit. The table shows the cost of ordering different numbers of foam hands. Can this situation be modeled by a linear equation? So that's our first step. We need to first decide, can it be written as a linear equation? And then we'll explain why. Then if possible, then we will write a linear model that represents the cost as a function of the number of foam hands. So then we'll write our equation. So the first thing that I did here, I'm going to do this with you, is I copied down the table and I used N for the number of hands, 4, 6, 8, 10, and 12, and then C for the cost of those specific number of hands, 34, 46, 58, 70, and 82. The first thing that we want to do here, we said we want to first determine, can this be modeled by a linear function? So I want to answer the question, is this linear? Remember, we did this back in chapter 3, and we need to know if it's a linear function or not. In order for a table to be a linear function, remember that it has to have a constant rate of change. So that's what we want to check here in our table, is does this table have a constant rate of change? So let's go through and let's see, in fact, if this table does or does not. First, let's check our x's. So our first x, this goes plus 2. Then our second set of x's, again, this is plus 2. Again, this is plus 2. And finally, this is plus 2. So our x's are good to go. Now let's check our y's. I want to figure out, how do I get from 34 to 46? Remember, we always want to add for a linear function. What are we adding by? So if this is hard for you to do in your head, all you have to do is subtract the second one minus the first one. So if I want to use my calculator, I could do 46 minus 34, and that change would be 12. So to get from 34 to 46, I would add 12. Okay, then let's find the second change. So if I do the second one minus the first one, 58 minus 46, again, this would be plus 12. Let's check this one, 70 minus 58, yep, that would be plus 12. And then let's do our last one, 70 to 82, that one's easy. That would also be plus 12. So we're ready to answer the first part of this question. Yes, it can be modeled by a linear function because the values have a constant rate of change. Okay, so that's our first part. Our second part now is, now that I decided my answer is yes, I can write a linear equation, let's go ahead and actually write a linear equation to describe this table. So to do that, I'm going to pick any 2 points that I want from this table, and I'll use the 2 points to write my equation. So I'm going to pick the first 2 points, these 2 points here. Let's write them as ordered pairs. My first point would be 4 and 34. And my second point would be 6 and 46. Okay, our first step is we want to find our slope. So we can find the slope by doing y2 minus y1 over x2 minus x1, like how we have been practicing in the rest of section 4.2. But because they gave me this information in a table, I can also just use the change in y over the change in x that I already found in my table. In my table, these y's were changing by 12 as the x's were changing by 2. So that would be my slope 12 over 2, which simplifies to 6. Now let's write an equation. I'm going to use point slope form and then turn it into slope intercept form. I'm going to use the first point as my x1 and y1. Let's plug this into point slope form, which is y minus y1 equals m times the quantity of x minus x1. We have y minus 34 equals 6 times the quantity of x minus 4. Okay, let's simplify and get this into slope-intercept form. We're going to solve for y. Let's distribute the 6 to both of these. Y minus 34 equals 6x minus 24. And then again, we're going to solve for y. We're going to add 34 to both sides. And I get my equation, y equals 6x plus 10. Now I can leave my equation like this, or in the beginning I said I was going to use n for the number of foam fingers, which is like our x coordinate, and y for the cost, which is like our y coordinate, c for our cost, which is like our y coordinate. So I can, instead of using x and y, I can use these variables too. So I can say that c equals, or the cost equals, 6 times n, 6 times the number of fingers, or hands, whatever we're talking about here, the foam hands, and then plus 10. So that would be our equation for this problem.